All right, welcome back. We're picking up where we left off. So we've talked about alkynes. We talked about how to name them, where they come from, and then how to prepare them, like so doing basically two elimination reactions on a dihalide. Now it's time to talk about the different reactions that you can do to an alkyne. So this is going to look a lot like what we did last chapter with the alkenes. And so we're picking up in section 9.5 in the third edition and 10.5 in the second edition. Okay, so starting off with the reduction of alkynes. So remember, when you look at a reduction in organic chemistry, you don't have to necessarily count up the formal charges or anything like that. What you're going to look at is look at your carbons and see how many hydrogens they're bonded to. If a reaction increases the number of carbon-hydrogen bonds, so like this carbon here is bonded to 0 hydrogens in the reactants, and then it's bonded to 2 hydrogens in the products. That's what we call a reduction. So this carbon has been reduced and this carbon has also been reduced. So that's what we talk about when we say reduction of alkynes to head up this section. So catalytic hydrogenation works on alkenes, like we saw in the last chapter, and it also works the same on alkynes. And let me expand this out to the full screen here. If you just use hydrogen gas on a platinum, palladium, or nickel metal surface, you'll go from an alkyne an alkyne all the way to an alkane. So that's great. If you have an alkyne and you want to take it to an alkane, no problem. But of course, when we're doing organic chemistry, oftentimes we want to be, we want to be adding things to a double bond. For example, we may want to take the alkyne to an alkene first. So we cannot do that just using hydrogen gas and platinum. Instead, we have to stop it in this intermediate step here. Just a minor point here, if you were able to stop it magically on this surface, you would produce the cis alkene because you have a syn addition of hydrogens coming from one side. And if you'll recall, that's because the heterogeneous catalyst, the platinum catalyst, you've got basically these hydrides sticking up on the surface of the platinum. And so those are both going to add from the same side. And that's why you get the syn addition for that. So again, as I mentioned, in a lot of times, we don't really want the alkane. Sometimes we do, but not all the time. So in order to do that, what we do is we can do what we call poisoning the catalyst or deactivating the catalyst. What this does is basically takes the catalyst and makes it just a little bit less reactive, right? So a poison catalyst means that it doesn't work as well because there's something stopping it from working. And we'll look at an example of what that mechanism looks like on the next slide. But there's two different catalysts we can use for the reduction of alkynes that will stop it at this cis alkene here. There's what's called Lindlar's catalyst, and then the nickel 2B complex, or P2. So Lindlar's catalyst basically is you take this quinoline, you put palladium in barium sulfate solution and methanol, and that is a way that you can stop this palladium surface basically from going from the alkene to the alkane. You just stop it at the cis alkene. Same thing with the P2. So you could do either of these here. And oftentimes you'll just write like Lindlar's catalyst. So you do H2 plus Lindlar's catalyst, or H2 P2. So the way that this works basically is like you poison the catalyst in such a way that it catalyzes the first step, but no longer catalyzes the second step. And the way that you can do this with the heterogeneous catalyst is basically you just set it up so that the alkyne is happy to lie flat on the surface, but for whatever reason, the alkene no longer is able to lie on the surface of the catalyst. Of course, this isn't something that you usually design. You just kind of have to play around with it until you find the right mix that does poison the catalyst and give you the cis alkene. So basically, yeah, you just get to this first step, and then the second step, not being catalyzed, is not going to occur without that catalyst. Okay, so that's catalytic reduction. There is also another type of reduction. It's not catalytic, but it is a way that you can get it. It's what's called dissolving metal reduction. This will take your alkyne and it reduces to the trans alkene rather than the cis alkene, which is what we just saw. So this is what when we look at this, you take your alkyne, you put sodium metal in ammonia liquid, NaNH3. So this is sodium metal, just like solid metal, and you dissolve it in NH3. It actually looks really cool. I'll try to post a photo of it. You can also look it up if you want to, just a dissolving metal reaction or sodium metal in ammonia. I'll try to post it in the lecture for this one, if I can remember that. And again, you take your alkyne, it produces the trans alkene. You would say that this is stereoselective for the anti-addition of H and H. So you basically take this, you're going to put hydrogen on one, hydrogen on the other. That gives you your trans alkene. So of course, why is this one trans and the other one is cis? As with all things organic chemistry, when you ask yourself, like, why is this product going to occur and not the other one? It's all to do with the mechanism. And so the mechanism that's proposed for the dissolving metal reaction is looks like this below. Basically, what happens is a single electron is going to transfer from a sodium atom to the alkyne. And what that's going to do is it's going to form a lone pair on one of the vinyl carbons here. And then the other one, this pi bond basically breaks. So you break a pi bond, that gives you your lone pair with the sodium electron on one side. And then the other electron that's in the lone pair is going to go into the empty p orbital on the other carbon here. So now all of a sudden you've got this weird setup where you've got your alkene. One side of the alkene has a lone pair. The other side of the alkene is a radical. Now this lone pair is going to be very basic. It's going to be basic enough actually to be able to deprotonate ammonia, which if you'll recall from the last lecture, that's hard to do, but this is much more acidic, so it's able to do that. Then you still have to clean up this radical here. This radical can be cleaned up just by adding another electron from another sodium atom that you have in solution. Then once you have a lone pair, that can all of a sudden be protonated again, and that gives you your trans alkene. So I think the trickiest part here is going to be the nucleophilic attack. The nucleophilic attack essentially of just an electron onto the vinyl carbon. That's kind of the trickiest one here. And again, just looking at it again, we have an electron coming from the sodium atom. If you look on your periodic table, you'll see that sodium has one valence electron. That one valence electron it's happy to give away. It wants to get rid of it so it can form the sodium ion. And that's exactly what happens. And yeah, so when you do that, of course, you have to break one of the pi bonds, otherwise you would violate the octet rule. So the one pi bond splits homolytically, one of the carbons getting one electron, the other carbon getting the other electron. The carbon that picked up the sodium electron now has a lone pair. So, okay, so we looked at that. I think we have another kind of like step-by-step look at it here. So yeah, again, I guess I should have moved to this slide so that we could take a closer look at it. Again, there's going to be an electron transfer from the sodium. We'll call that a nucleophilic attack. An electron is a nucleophile, right? It's got a negative charge, so that makes sense. Now, in order to do that, that's going to break the pi bond, break one of the pi bonds. That pi bond breaks homolytically, giving a radical on one side and then forming a lone pair on the other side. Now, this is the key. This is why it's actually beneficial to form the trans alkene rather than the cis alkene. If you had it set up so that in this case you form the cis, where you have the radical on one side and the lone pair on the other, these have strong negative charges and they're going to repel each other pretty significantly. So this is a much higher energy intermediate that forms. So this intermediate here is a much lower energy intermediate, and so this is going to be more likely to occur. And basically that forms the geometry from there. The lone pair then gets protonated. The radical becomes a lone pair from another sodium electron and then protonates itself. That gives you your trans alkene. So that's that mechanism. I think we've only got one other mechanism that's any difficult at all. So just spend some time, make sure you can write that mechanism out, but you should be good. Okay, so this gives us like a little bit of flexibility here. Hopefully these synthesis charts are getting more and more familiar to you, but basically you can take your alkyne. If you react it with hydrogen on platinum, you're gonna get the alkane. If you use H2 and the Lindlar's catalyst, that gives you the cis alkene. If you use sodium in ammonia, that gives you the transalkene. And then either of those alkenes can be then further reduced to the alkane, just using the stuff that we used in the previous chapter, which is, again, hydrogen on platinum. Okay, so that was reduction. Just like with alkenes, there's going to be like a series of reactions that we'll talk about. Not each of them is going to have a mechanism you need to memorize or anything, but I'll make sure to point it out when you do need to know the mechanism. These should look familiar because they're basically addition reactions, and they're just addition reactions that are occurring on alkynes rather than on alkenes. So, okay, so hydrohalogenation. This is basically where you add an H and an X across a pi bond, and it adds to the Markovnikov in the Markovnikov fashion. So in other words, you're going to add the halogen to the more substituted carbon, and the hydrogen goes to the less substituted carbon. Same thing is true when it happens with an alkyne. So here, so that should be kind of familiar up here with the addition to the alkene. Take an alkene, react it with HX. The proton transfers to the less substituted carbon, which in this case is the terminal carbon. The X is going to be bonded to the more substituted carbon, the neighboring carbon here. Looks like that. Same thing happens with an alkyne. The only difference is when you break the pi bond for this addition, you're still left with one pi bond over. So it's just an alkene that's also then bonded to a halogen. So it's like a haloalkene, you can think of it that way. Right, again, the X is going to add to the more substituted carbon. That's this one here. The hydrogen is going to go to the less substituted carbon, which in this case is the terminal carbon. Now, once you're here, of course, you still have an alkene. This alkene can do another hydrohalogenation. So if you use excess of the HX, you're going to go all the way and form another dihalide. And in this case, think it through. HX is going to add Markovnikov, right? So the X goes to the more substituted carbon. That's the carbon that's already bonded to X. So you're going to end up with a dihalide where both halogens are bonded on the same carbon, or what we call a geminal dihalide. Remember, geminal means like twinned. So it's like they're bonded to the same carbon, like they're twins, basically. Yeah, so the now if we knew that the mechanism was the same as what happened with HX addition, it would form like a vinyl carbocation. So don't write this down in your notes or anything. We're just kind of like exploring it, you know, what would happen. So this is the analogous way you draw a nucleophilic attack, or basically a proton transfer of a proton from the HX to the carbon-carbon pi system. That forms a vinyl carbocation, which then is subject to a nucleophilic attack. But I hope you remember, vinyl carbocations are extremely unstable. So this is not likely to occur. It doesn't seem like this would be the mechanism. So it's got to be something else going on here. Now, with a lot of reactions, mechanisms are kind of speculative. We can't totally know everything about a mechanism because we can't like shrink ourselves down and like watch the molecules actually interact. We can just do our best to guess based on kinetic data. And so when we look at the kinetic data, we actually find that the rate law of this reaction, so the rate of this reaction is first order with respect to the alkyne and second order with respect to HX. This is a very rare, what's called a termolecular process, where the transition state or the rate determining step involves 3 different molecules. You may remember from your Gen Chem 2, that's really unusual. So something weird is going on here. So this is the proposed mechanism. You don't have to memorize this necessarily, but it is kind of useful to help understand. Basically, what happens is the transition state has to involve 3 different molecules, 2 of the HXs and 1 of the alkynes. And so the idea is here basically at the same time that you have a transfer of X to the one side, you're also at the same time breaking one of the pi bonds and forming your proton transfer on the other end. So this is kind of like the proposed mechanism here. But as I mentioned, there's no proof that this is the case. We can't watch this happen, so we don't totally know. And so it is possible that there's other mechanisms that are working as well. So we don't really know. Okay, so now that was hydrohalogenation. Now, if you remember, if you do hydrohalogenation in the presence of peroxides, that's this ROOR down here, these will add anti-Markovnikov. So in other words, rather than having the H go to the less substituted carbon, now it's going to go to the more substituted carbon. The bromine goes to the less substituted carbon. In this case, you could form an E or a Z isomer. So as it turns out, you get both of them. Just to keep that in mind, you can get either the E or the Z. So just keep in mind. This is a radical mechanism. It's going to be one of the first ones that you talk about in OChem 2. And just keep in mind, this only works with HBr. So you don't do this with HCl or HI. Okay, so real quick, hydrohalogenation of alkynes, that's going to be the reverse of the elimination of the dihalides. So basically, you can present an alkyne with excess HX, whichever one it wants to be, specifically HBr or HCl, as you may recall from last chapter. That forms the dihalide, a geminal dihalide. In the presence of excess of a strong base, so it's usually sodium amide in ammonia, you can then do the elimination reaction and form your alkyne. The second step here for water, it's just to protonate any terminal alkynes that you have. Okay, so hopefully that makes sense. Again, don't worry about necessarily memorizing those mechanisms. We've done a lot of the memorization of mechanisms for alkenes because those are better understood. Alkynes, not as well understood. You do need to know the reduction mechanism for the metal, and then there's one more mechanism we're going to study down here. So just let's get to it. Okay, so alkynes, like alkenes, can undergo hydration reactions as well. That's where you add an H and an OH, either Markovnikov or anti-Markovnikov. Now, if you just use acid with an alkyne, it's a very slow reaction. So if you use a mercury 2 catalyst, like mercury 2 sulfate, that will speed it up quite a bit because this one is going to form a vinyl carbocation, as we're about to see. Now, one thing to keep in mind here is that there's an issue with what happens. So if I told you that, okay, you add H and OH to this alkyne, in a Markovnikov fashion, that would suggest that you've put a hydrogen on the terminal end of the alkyne and an OH on the second one here, the more substituted carbon. That would give you this. Now, this is called an enol. Okay, so an enol is just exactly like it sounds. It's an alkene with an alcohol, and they have to be bonded. They're in the same system here. Now, the thing is, enols are less stable than a very closely related compound, which is a ketone here. So the enol is going to undergo what's called tautomerization. Okay, tautomerization is kind of like resonance, but it's with structural isomers. So basically, there's just a very simple and quick reaction that can occur to take the enol to the ketone. And because the ketone is more stable, the ketone is going to form 90% of the time. So it's going to be predominant basically in the mixture here. We'll look at what that looks like here in a second. So, but I just want to keep in mind, even though you would think you form this enol, basically the enol is not stable relative to the ketone. So the ketone is what's going to form. Okay, so here's the mechanism. So the first part of the mechanism is we have a nucleophilic attack from the alkyne, the pi bond, onto the mercury 2 cation. That forms your mercurinium ion. Now this mercurinium ion has the unfortunate side effect of having a vinyl cation. So that's not great, but that is just one of the, that is just the case here with this reaction. Now, this vinyl cation is strongly electrophilic. So water can then attack this vinyl cation and form your new carbon-oxygen bond. Then what's going to happen is you have your protonated alcohol. This is very strongly acidic, so that's going to pass its proton on to another water molecule just in a proton transfer. And that gives you your enol with the mercury still kind of attached here. So getting rid of the mercury, what happens is you can just replace the, it's just going to replace the mercury with the proton just from the proton that we just gave away right now. So basically what happens is you do a nucleophilic attack from the pi bond onto the proton. So you basically do a proton transfer to the pi bond. That's going to form a carbocation, and then this carbon here has 2 hydrogens bonded to it. Well, this carbocation is bonded to a more electronegative element. So this more electronegative element with a lone pair can form a pi bond, which is exactly what occurs. So this is a resonance form here. So we just go through resonance, and then finally, this mercury ion can be eliminated, and as it's eliminated, that forms the enol here. So the mercury ion goes away, the mercury carbon bond is going to form the new pi bond that we're going to regenerate here, the alkene. And then at the same time, because we have to kind of preserve we have to follow the octet rule here, this carbon oxygen pi bond is going to form a lone pair on the formal positive charge oxygen here. So again, this gives the enol intermediate here. Okay, so now I mentioned this before, but this enol is not stable relative to one of its possible tautomers. Okay, so tautomerize or tautomers. Tautomers basically are structural isomers that can interconvert through a chemical reaction. So even though they're not the same molecule, the bonding is different, but they do have the same number of carbons and oxygens and hydrogens, so they are structural isomers. So that tells us that they're relatively similar. The difference is, you have a carbon-carbon pi bond over here, you have a carbon-oxygen pi bond over here. Oxygen-hydrogen bond here, no oxygen-hydrogen bond here. So yeah, so this ends up being sort of an equilibrium reaction that occurs, where if you have a proton transfer from enol, that forms your carbocation. That carbocation can then form, a protonated ketone, and then this protonated ketone can give away its proton to give you the ketone. So, and you can do this either way, right? I mean, so this ketone can then be protonated. Once this is protonated, then you can form the carbocation, and then the carbocation can undergo an elimination reaction, and you get your enol. So either of those are possible. However, the ketone is more stable, so generally speaking, you're going to end up with the ketone here. So that's just kind of like the final product here of this reaction. Okay, so that was for like oxymercuration, basically, the similar reaction. There's also hydroboration-oxidation of alkynes, works in the same way. Remember, hydroboration-oxidation is regioselective for the anti-Markovnikov addition of H and OH for alkenes, and the same is true for alkynes. That means it's going to install the OH group on the less substituted carbon. And in this case, because we have a terminal alkyne, when we tautomerize our enol, this enol actually tautomerizes to an aldehyde. So just keep this in mind. Now, this tautomerization has to be catalyzed by a hydroxide. Otherwise, it does have a stopping point here until you add a base. But the enol itself isn't usually as useful as the aldehyde. Okay, so again, don't worry about the mechanism for the hydroboration oxidation of the alkyne. I know you had to do it for the alkene already, so don't worry too much about that mechanism. However, the base catalyzed tautomerization is worth a look here. What happens first is you put your enol into a base that's going to deprotonate the enol and give you the enolate ion. Now, the enolate ion is in resonance with a carbanion. This carbanion can then be protonated from just a water molecule lying around, and that would give you an aldehyde here. So just keep in mind this enolate is just a formal negative charge on the oxygen. Deprotonated enol is the way you can think about it. And just keep in mind that if you do use BH3, you can actually do 2 successive additions, so you can get more and more of that. So that would be not good, right? Because we have already a borane here, and then we get another borane. That's not what we want. So what you do is basically you take something that's a dialkyl borane, like in this case 9-BBN or di-ICML borane. Either of these will work just fine. Basically, it prevents the second addition of a borane, and that way you only get the single hydration product. So yeah, and basically what you do here is you take your alkyne. You put it in with one of these boranes that we just talked about. I usually use 9-ppn because it's easier to spell, but your book, you could also use diisocyanamyl borane as well. And that gives you your aldehyde. So yeah, so kind of summing everything up, when you take your alkyne, if you have a terminal alkyne, you do Markovnikov hydration, which is acid catalyzed with this mercury 2 catalyst. That gives you the methyl ketone in this case. If you do the same thing, but you use your substituted borane and hydrogen peroxide and sodium hydroxide, again, that's hydroboration. That gives you the aldehyde product. Okay. So yeah, so I know that was a lot to go over, but you mostly don't have to worry about the mechanisms. Just worry, so you do need to know this mechanism here for the mercurinium ion formation, and then know the keto-enol tautomerization, be able to draw these mechanisms here as well. Okay. Okay, all right. So finally, for this lecture, we have halogenation. Now, if you halogenate an alkyne, you can halogenate it twice, right? You basically halogenate the first pi bond, you're left over with the pi bond, you get halogenate the second pi bond, that gives you 4 total halogens there. So you can get, basically a tetrahalide 4 substituted on the halogen. Something that's interesting is you can do it so that you get just one addition. You basically get your alkene, where you have both the E and the Z product here. Just keep in mind that when that occurs, like you get both of these products here. So something's going on with this mechanism that we don't totally know. I mentioned before that there's some of these mechanisms that haven't been fully explored. This is one of them. Again, you don't have to know the mechanism because we don't really know the mechanism. Because if it were analogous to the halogenation of alkenes, we would only get the anti-product, so this one. But in fact, we do get this syn product. So that means that something else is going on here altogether. So just keep that in mind. You can get the tetrahalide if you use excess of the halogen, or if you just use one equivalent, that gives you the dihalide on the alkene. Okay, so that's it for part 1. We've got a handful of other reactions we're going to talk about, and then strategies for using those reactions in the next lecture. So go ahead, do some more practice down below. Get used to drawing out some synthesis problems, and then in the next lecture, we'll talk more about what to do with those. So, okay, I'll see you very soon.